Alrighty, so happy Wednesday.
Oh, wait. That money you're gonna ask, yeah, we're gonna have that.
I need to know so I can mentally start preparing myself. And actually like start preparing the things.
Now, I do think I'm gonna bump it out off to after Thanksgiving, because I don't want to go through like the urban theory too fast.
Thank you. Well,
So we'll do, but you don't, whatever you do, don't use Monday as an extra day for Thanksgiving, to make Thanksgiving a 8-day vacation.
it's not because we have Tuesday left.
I know, we have Monday and Tuesday, we have class Monday and Tuesday.
I was gonna be gone on Monday, but I'm not now.
Boy, we made varsity, yes, so excited as a
Basketball?
sophomore. Yeah, basketball, so excited for him.
Where at?
So,
Amherst, the little school. But nonetheless, it's kind of
actually kind of cool. Who? Josh Johnson?
You're Josh? That's our buddy.
So cool.
he's your roommate?
Oh, he's so cool. Yeah, Josh is super cool. There's a couple Mitch, Deidre also. There's some Ambrose grads here. Sasha. This is Ambrose grad.
But anyway, I'm really excited. So we were going to go elk hunting. We are still going to go elk hunting, but I was
You
going
said
to come back
whale?
late Monday night. Elk. We're going to go elk hunting. We're going to go kill big bear.
I heard, I'm not the only one. I swear you said well.
We're going whale hunting.
I heard
That's
where?
what I do on my free time. I climb mountains and I hunt whales. Right?
See, I'm not the only one. The other people heard whales.
Whale hunting.
I swear.
Hunting. And I was going to come back Monday night late, but not more. Because he can't just practice. There you have it. Okay, how are we doing on Vesper? Any questions on Vesper before we complicate it? Because it does get a little bit more complex.
Oh, what? No. Can you go?
Yes.
over
Let's make it, keep it where it is. Keep it where it is.
Hybridization is something I'm a little shaky on still.
Yes, I am going to make hybridization so easy for you.
Okay.
Okay? But you have to trust me. You can't make it more complex than it is, because it's really counting from 2 to 6. Again, that's all we've done, right? We all counted from 2 to 6 on Monday. When it was 2, it was linear. When it was 3, it was trigonoplanar. When it was 4, it was tetrahedral. When it was 5, it was 5 was the weird one, trigonal bipyramidal, and it was 6, it was. Okay, so you want the big picture of hybridization? It's just as easy. How do you count to 2?
1, 2.
Yes. SP.
Oh.
How do you count to 3?
3, 4.
SPP. Oh. How do you count to 4? SPPP. How do you count to 5? Oh, we ran out of P's, right? Because there's only 3 of them. So what are we going to do? SPPPD. How do we count to 6? Not very complex. SPPPDD. Okay? So here's why. Once we get past 2P, these only have 2P. They don't have 2D. There's no such thing. They're done. They have nowhere to go. That's why they always obey the octet rule. But once I go here, now, yes, I can stay in the 3p orbital. But I also have dropped down into the d orbitals. So phosphorus and sulfur said, well, I could just mix those d orbitals as well. And it does. They do. So that's it. That's hybridization. Okay, it's not complicated. We just have to be able to count. Just like I don't think linear, trigonoplanar, tetrahedral, trigonal bipyramidal, octahedral, linear, trigonoplanar, tetrahedral, trigonal bipyramidal, octahedral is that difficult. I really don't. Neither do I think SP is. SP2, SP3, SP3D, and SP3D2. Okay, it's just counting from 2 to 6. That's all it is. Okay? Now that said, how does that become then practical? Well, that's what we're going to see today. There's our principal or our basic or our main geometries. Okay? We call those our electron domain geometries. They differ from molecular geometry. How? What does molecular geometry ignore? Lone pairs. And I always say, is it good to ignore those? No, it's not, but we do. Okay? Because they play a big role in the overall electron arrangement of molecules. So I don't think we should ignore them, but we do. And so that's where we get this second set of kind of funny names, okay? Again, these are my electron domain geometry, or my principal geometries, 2 through 6. Once I know that, then I look at the molecule and I say, okay, well, how many lone pairs are there? If there's one lone pair and two bonding pair, then it's bent or angular, okay? If I'm principal geometry of a tetrahedron and I have 1 non-bonding and 3 bonding, then I'm trigonal pyramid or trigonal pyramidal. Okay? If I'm 2 non-bonding and 2 bonding, I'm back to bent or angular, just like water. So this is water, this is ammonia, and this is methane. Okay? And you can see the approximate bond angles here, about 109. Here's our fun one. We did trigonal bipyramidal. If I have all the same bonding, all 5 of them are bonding, it's trigonal bipyramidal as my principal. But if I have 1 lone pair, it goes on the equatorial plane, not the axial plane. We talked about that because it gives it more room. And this whole thing is about electron pairs like to be as far away from one another as possible. Non-bonding take up more room than bonding, so we put those on the equatorial plane. We call this sawhorse or seesaw. Okay, just exactly what it is. Because if you set it on its side, it goes back and forth just like a seesaw. All right. If we remove 1 more, it also comes off the equatorial plane, so that forms a T shape. And if we take 1 more off, it's coming off the equatorial plane, and so that becomes linear. All right. So these are all those geometries, and you probably had to memorize those at some point if you've had chemistry before. If you hadn't had chemistry, I think they're pretty intuitive and pretty straightforward. Octahedral, all 6 of them. Bonding, it's also octahedral. But if I have 1 non-bonding and 5 bonding, then it becomes square pyramid, all right? So it becomes a square pyramid. If I have 2 non-bonding, well, I'm gonna put those on the axial plane because that's farthest away with those non-bonding, that pair of non-bonding electrons, and so that becomes square planar. If I take off a third, so I have 3 electron non-bonding, 3 bonding, and again, we're back to T shape. Oh, well, that makes sense because it's a T, okay? And if I have 4 non-bonding and 2 bonding, it's linear. So there you have it. That's Vesprit theory, okay? So let's utilize that and let's actually use this. So when we look at a couple examples of this, electron domain of 2, you'll notice that one of our examples of this is carbon dioxide. So if I make an electron dot structure of carbon dioxide, it looks like this. And what's the farthest away 2 electron domains can be off a central core? Well, linear. Okay. Hey, guess what? Linear is 2. How do I say 2 in hybridized orbital sets? Oh, I say sp. That's 2. So this is going to be an sp carbon, and I would be correct in that. Okay. Now oxygen is not sp. What is oxygen? What is oxygen right here? How many electron domains? 3. Then what is it? sp2. Don't make it harder than it is. spp. Okay? That's it. That's all hybridization is. It's just explaining where those electrons are coming from. Okay? Remember, n equals 2 has the 2s and 3 2p's. They're close together, and they mix, and they will. We'll see that, especially when we get to carbon, which is the master of hybridization. Okay? Notice with my 3 domains. 3 domains, my principal or my electron domain geometry is trigonal planar. Notice if it's all bonding, for example, boron trifluoride would be an example of this, then it looks like this. Well, notice if I'm 2 bonding and 1 non-bonding, something like nitrogen dioxide, I am angular or bent, and you see that there, okay? So what is my hybridization of boron here? sp2, spp, it's 3. Electron domain geometry of 3 has to be spp, so sp2, okay? What's my hybridized orbital of fluorine? sp3. Why? Because there's 4 electron domains, or 3 electron pairs and 1 bonding. Okay, so it's spp or sp3. Okay. When I go to Oh yeah, this is kind of the graphic to show the exaggeration of non-bonding versus bonding. I kind of verbally explained this on Monday, but you can see that non-bonding takes up more room. So it's typically why we do see a skewing of those non-bonding electrons. They just take up more room. So when you do see the three molecules that are really the main molecules that we build to kind of explain this, you have 109.5, you have 107, and you have 104.5. And it's just that non-bonding pair of electrons is pushing on those hydrogens, and it skews them away from that non-bonding pair of electrons, okay? And so this is kind of the classic or historic way to view and why we believe that the non-bonding electrons take up more room than bonding electrons, okay? Another example of this would be this molecule here with the carbonyl, the chlorines, okay? The chlorines are actually skewed together, which is kind of interesting because chlorines are bigger than hydrogens. So you can see that this is 111.4, whereas this, instead of being 120, is 120.4, or 124.3. And the reason for that is, don't forget, there's a massive pair of electrons right here on oxygen, and a massive pair of electrons here, and they're pushing on those chlorines to skew those out of their 120, which is what they prefer for trigonal planar, okay? So that's that overall effect that we do see. Now, when we get to the tetrahedron, our electron domain geometry of 4, if it's all 4 bonding, then it remains tetrahedral. Example of that would be methane. If we have 3 bonding, 1 non-bonding, example of that, again, what we just saw, is going to be ammonia, okay? And if we have 2 bonding, 2 non-bonding, example of that's going to be water. What is the hybridization of the electron domain of tetrahedron? sp.p.p, so sp3. Okay, yes?
Are orbitals always hybridized?
Ooh, in the ground state, no. So carbon in its ground state is an amorphous soot, it's just carbon. It remains 1s2, 2s2, 2p2. When carbon starts to bond, it will either be sp3, sp2, or sp. You have alkanes, alkenes, and alkynes. Okay? So, and that's kind of one of the difficulties with understanding carbon chemistry. Yeah, but as a ground state, see, here's the cool thing. You can also photo excite these things. You have what's called end-of-pi star and pi-to-pi star transitions when you start to excite these electrons. But when we make molecules, for the most part, we're talking about hybridized orbitals. Okay? So tetrahedron, trigonal pyramid or trigonal pyramidal, and then finally we go back to bent. Okay? When we get to 5, again, you have your axial plane here, and you have your equatorial plane. So if you looked at a molecule like sulfur tetrafluoride, let's do that one together. So if I asked you, what is a couple different things? What's the electron domain geometry? What's the molecular geometry? And what is the, what else could I ask you? What's the hybridization for sulfur tetrafluoride? So if I'm going to do sulfur tetrafluoride, I'm going to look at the periodic table. I'm going to say it's got 6, just like we've been doing. I'm going to say it's 4 times 7. So it has a total of how many electrons? How many? 34 electrons. Okay. So the central atom on this is going to be sulfur because it's a lower what? We good? Okay. So with that, am I correct? 28 plus 4 is 34. Okay. So sulfur. It's going to put a fluorine here with its 8 electrons. It's going to put a fluorine here with its 8 electrons. It's going to put a fluorine here with its 8 electrons. It's going to put a fluorine here with its 8 electrons. And if you do that, I am 8 times 4, so I'm 32. I have 2 to go. Oh, well, sulfur just does this. So there's sulfur. Okay? So my electron domain geometry for sulfur is 5. Right? Because I am 1, 2, 3, 4, 5. So I'm trigonal bipyramidal as my electron domain. But what am I as a molecule? What is my molecular geometry? Seesaw. Good. Because I ignore that, and it becomes seesaw. Okay? What is my hybridized state of sulfur? sp3d. Good. Excellent. Okay, 1, 2, 3, 4, 5. It has to be S, S, P, 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 D. 5. SP3D. Okay? And that's what happens. Sulfur actually puts electrons, mixes electrons out of that 3D. Okay? So you can see that that's how we actually use this to do predictions for structure. Okay? So it, again, because it has more room on the equatorial plane, it prefers to put the non-bonding pair in the equatorial plane. Okay? Very cool, right? Yeah, so there's sulfur tetrafluoride. Our last one, oh no, this is our last one. This is trigonal bipyramidal. So trigonal bipyramidal, you can see that again, it's an sp3d. Examples of that, if it's all bonding, it's going to be phosphorus pentachloride. An example of the seesaw we just saw was sulfur tetrafluoride. Okay. Chlorine trifluoride would be an example of the T-shape with 3 and 2, 3 bonding, 2 non-bonding. And finally, one of my favorite is xenon difluoride, which is, again, trigonal bipyramidal, has 5, so that xenon there is an sp3d, and it has 3 non-bonding pairs of electrons that it puts around the equatorial plane. So it's linear. And it's actually non-polar. Kind of cool, right? And we'll talk about polarity here in a second. Okay? Lastly is our octahedral. And so here's an octahedral. Example of an octahedral molecular geometry would be sulfur hexafluoride. An example of 5 and 1 or square pyramidal as my molecular geometry would be bromine pentafluoride. And again, back to xenon, an example of 4 and 2 or square planar would be xenon tetrafluoride. Okay? And we can figure all those out. You don't have to memorize those. You just, if I can draw a good electron dot structure, then I just count the electron domains, and it tells me what my principal geometry is or my electron domain geometry is. If I have lone pairs, that tells me what my molecular geometry is. It also tells me what my hybridization is. What's my hybridization on that xenon right there? sp3d2, yep, because it has 6, and the only way to count to 6 is sppppdd, okay? So sp3d2, that's it. So hybridization isn't more difficult than that. That's where we believe the electrons are coming out of and how these orbitals mix, okay? So there you have it. So we get octahedral. If it's still 6, we get square pyramidal, square pyramid. We get square planar. We also get T-shape, and we also get linear. It just keeps on growing. So with 6, it's just a little bit more difficult. Yes, there are those beyond 6. There are 7, which I'm not going to hold you accountable for, but I just want to show you that they do go out there. There are some funny compounds that typically deal with the Nobel gases. It's some really electronegative atoms like oxygen and fluorine. So these would be 2 examples of a 7 electron pair geometry, and it's kind of a bizarre looking thing, and trying to do some calculations on where that exists spatially is kind of an interesting thing for an inorganic chemist like Dr. Harris to work on. So you can see that you have that. You also have xenon hexafluoride, which is believed to look something like this. So you can see it's 1, 2, 3, 4, 5, 6. Wow, that's kind of cool. Fluxional process. There you go, a great word. So there you have it. 8. There you have 8. Kind of cool. Isn't that kind of neat? Square antiprism. So beyond the octet or the octahedral, you have a couple options out there. Okay. But for us, we're going to go from 2 to 6. That gives us the basis. These are kind of anomalies. That gives us really the basis of pretty much all the life chemistry that we will see. Nitrogen, oxygen, fluorine, phosphorus, and sulfur go up from 2 to 6, and boron even, and carbon. Carbon's the most important. Yeah. Okay. So there you have it. All right. This is what we use then to begin to build larger molecules. So in lab yesterday, did you work with the model kits? Yes. Yeah. So those are called Molymod model kits, and we purchased those years ago for exactly what you did yesterday, which was really to build molecules. So to take something like carbon and to say, what does carbon actually look like, and actually see it with your hands, see what it actually looks like, what we believe it's going to look like, that is. And you can see something like carbon tetrachlorine or tetrafluoride or something like that would look like this. And so we can begin to build, this up here happens to be acetic acid. This is the acid that's found in vinegar. And we can predict with this. And we can say that carbon there is an sp3 carbon. Why is it an sp3 carbon? Oh, it's an sp3 carbon because it has 4 bonds, okay, or 4 electron domains. So it's 1, 2, 3, 4. What's my hybridization of that carbon? What is it? Yeah, it's 3, so it's sp2. Good. Okay. What is my hybridization of that oxygen? sp2. Good. 3 electron domains. Right? 1, 2, 3. What's my hybridization of this oxygen? sp3. See how this works? It literally is counting from 2 to 6. Don't make it more difficult than that. Okay, that's really all it is. sp, sp2, sp3, sp3d, sp3d. Okay. And we can use this also to predict bond angles, which is actually really kind of cool. So if a theory is good, you can use it to predict, and we can. So we could come up with a fairly good idea of what the molecule of acetic acid would look like, okay? Using a molymod kit and based on valence shell electron pair repulsion theory. Okay, pretty cool. So there's acetic acid. Here's probably more likely what it looks like. Again, atoms probably aren't colored, so we just do that as we typically make nitrogen blue, carbon either black or a dark gray, because that's kind of a soot, what it actually looks like. Hydrogen's typically a light gray or a white. Oxygen's typically red. Fluorine's typically like a purple. Chlorine's typically like a green. Bromine's usually an orange or yellow. And sulfur is yellow. Phosphorus is like a brown. So that's just kind of the colors that we use when we're building these kits. So you can see even like this kit here uses that. So you can see that's actually sulfur because it's yellow. So I don't know if you built sulfur yesterday. And this is phosphorus because it's kind of this rust color. So that's the kind of the convention that we have with these little building kits. But that's probably more what we think of with acetic acid. Okay. All right. So we've been all the way to here. We've even gone step 4, which is hybridization. I'm going to teach you hybridization again. I don't think it's difficult as long as we keep it simple and kind of explain what's going on there, at least what we believe to be going on there. So the very first thing we did is I wrote a symbol for a molecule on the board. We counted its electrons and we assigned it an electron or a good Lewis dot structure. That's what we did first. There's our Lewis structure. From that, we decided our electron domain geometry, our principal geometry, which is how many electron domains are coming off the central core. And in this case, there were 4, so that means it's tetrahedral. Okay. Next, we asked ourselves how many are bonding, how many are non-bonding. We ignored the non-bonding, and we gave it a new name. It's molecular geometry, which is trigonal pyramidal or trigonal bipyramidal. Okay. I then took it one step further, and I asked you, how do I count to 4 in hybridized orbitals? And you said sp3, because it's sp-pp. Okay? And our last step that we're going to do with this, before we jump into a new theory, is we're going to ask, is it a polar molecule? Okay, so this is where we have to talk about tug-of-wars in 3-dimensional space. All right? So, polarity. Is that molecule polar? So here's the way I want to look at this. I want to look at this molecule and say, this nitrogen has a certain electronegativity associated with it. And I know what that is because I've done the work of looking at the periodic table saying it's 4, 3.5, and 3.0. So I know the electronegativity of that nitrogen is 3.0, and I know the electronegativity of that hydrogen is 2.1. That tells me that I have a delta En of 0.9 between those nitrogens and those hydrogens. Okay? So that nitrogen is actually tugging on those electrons. Okay? But here's the thing. Is the tug equal? Does that nitrogen feel a tug from, or excuse me, does that hydrogen feel that tug differently than that hydrogen, differently than that hydrogen? No, those are all the same. But do those hydrogens feel that tug differently than an electron pair? And the answer is yeah, they do. Very different to have an electron pair than to have a hydrogen. Therefore, ammonia is a very polar molecule. Okay? So this is where we get into this whole, I'm going to go back here, not here. I'm going to go back here. When I begin to look at these molecules, I want to ask myself, are they polar? And I want to answer that with, are the electrons being delocalized around that central atom differently? Because if they are, it'll be polar. That's what a pole is, right? If electrons move, where they move to is negative, where they move from is positive. That sets up that pole. It makes it polar. So when I look at a molecule like sulfur hexafluoride, and I say, oh, wait a minute, that is like a six-way tug-of-war. All those fluorines are really polar. They're polar bonds. I mean, look at fluorine versus sulfur, right? I mean, you're 4.0 and here you're 2.5. So you're 1.5. You're in the polar covalent category of that sulfur fluorine bond. But because all the fluorines are pulling equally in all opposite directions, that's a nonpolar molecule. Does that make sense? But when I jump down to bromine pentafluoride, yeah, again, bromine pentafluoride, that's a really polar bond. I mean, I didn't tell you what this one is. This one's 2.8. But 2.8 versus 4.0, it's a pretty polar bond. Okay? So that fluorine, those fluorines are really tugging on that central bromine. But is the tugging equal? And why is it not equal? Yeah, because there's no fluorine down here to tug equally. Therefore, yeah, that's a very polar molecule. Okay? Because it's not equalized out. What do you think about xenon tetrafluoride? Do you think that's polar or nonpolar? And why? Why nonpolar? It's equal out. Yeah, all the electrons on the equatorial plane are pulling equally. The fluorines are pulling equally on the axial plane. Therefore, it's a nonpolar molecule. Okay? And you can see how you can start to predict that based on where these electrons sit. Okay, and if we go back one more, what do you think about that one? You think phosphorus pentachloride's polar or nonpolar? Nonpolar, right? All the equatorial fluorines are pulling, the axial atoms are pulling equally. That's a five-way tug-of-war where everyone is equal. So that flag or the handkerchief or whatever doesn't move. Okay? What about on sulfur tetrafluoride? Good, it's polar. You bet. The tug-of-war is not equaled out. It's got a lone pair out there that negates the tug of the fluorines on that central sulfur. What about chlorine trifluoride? Good, polar. And finally, what about xenon difluoride? Non-polar. See how this works? So you have come full circle. Now you know you can look at a molecule. You could look at a molecule like this xenon difluoride. You could draw a good Lewis dot structure. You could draw an electron domain geometry because you know where the electrons, the non-bonding and the bonding go. You can now know its molecular geometry. You know its hybridization. What is its hybridization? How do you count to 5? SPPPD. Okay, that's it. Don't make it more complicated. SP3D. All right? And I now know its polarity. Even though the bonds are polar, it's a nonpolar molecule. That's actually a lot.
But can I get like this stuff? So, right, if you have different atoms,
Yeah.
then it gets more
Yeah.
complicated.
So, for that very reason, let's see if we, as a class, can do that assignment with this molecule. Okay, you guys do it as a class. See what you get. You tell me, I want to know its molecular, I want to know its electron domain geometry. I want to know its molecular geometry. I want to know its hybridization, and I want to know whether it's polar or not. Okay? Your turn. I want to do. Your turn. Let's crank it up a notch. Do that one. Do that one and do this one. Do both those. This is fun. This is a teaching moment. Wait a minute.
That's the molecule. Yeah, I think it's spread. Okay, and that is.
Give you the stare down.
Yeah, both.
You said and hybridization.
Yes, hybridization as well. Polarity, hybridization, molecular geometry, electron domain geometry.
And then you've got chlorine going out, and chlorine is coming at us. Yep. Yeah, because they're gonna look the same. It's just gonna flop with the fluorines are gonna go around, and the chlorines are gonna. Yeah, and they are the same shape. It's just like
Ooh, I like the discussion. You get it? We have an opinion?
Right, never.
Okay, let's do it. Okay, so how many electrons total do we have for these? 5 times 7 is 35 plus 5 is good, 40. So we should have 40 electrons. So central atom, phosphorus.
Yep.
And I got a bunch of chlorines on this thing, right? Chlorine, 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 fluorine, and fluorine. So there's my Lewis dot structure. Now, that tells me a couple things. First off, one more. It tells me my electron domain geometry. What is it? Okay, it's trigonal bipyramidal. Okay, trigonal bipyramidal. What is my molecular geometry? It's also trigonal bipyramidal. What is my hybridization? How did I count to 5? sp3d. Okay. Now, here's what I have to ask: is it a polar molecule? Who says it's polar? Who says it's not polar? Okay, so not polar is winning out. How would I know that? Well, I've got 3 atoms of chlorine, and I've got 2 atoms of fluorine. What is larger, chlorine or fluorine? Why do I know chlorine to be larger? Because we already went through sizes of atoms, and I know if something's lower on the periodic table, it's larger. Okay? If it's to the right, it's smaller, but if it's below, it's larger. So I know chlorine is larger than fluorine. What does the entire valence shell electron pair repulsion theory deal with? Electron repulsion. Okay? That's the theory. Size. So if I'm chlorine, I'm a larger atom, therefore I want more space. What has more space? The equatorial plane or the axial plane? The equatorial plane. That's why if I have a lone pair, I'm larger, I go to the equatorial plane, not the axial plane. Remember, this is 90 degrees. This is 120. That gives me more room. So if I have a larger atom, I'm going to prefer to put my chlorines in the equatorial plane and my smaller fluorines in the axial plane. Therefore, am I polar or am I nonpolar? I am nonpolar. Why? Because all the equatorial chlorines are pulling equally on the phosphorus, and the fluorines are pulling equally on the phosphorus as well. It's a non-polar molecule. But what does that do for phosphorus dichlorotrifluoride? What do you think? Polar or non-polar? Makes it polar. Because now I no longer have an equal tug. I now have a situation where one of the fluorines is going to go into the equatorial plane, okay? Two of the fluorines go to the axial plane, giving me a non-pulling equally of the electrons, okay? So that's why that one's non-polar, that one's polar. Okay? Not very polar, but it's polar, okay? Cool, we're good? And we just use a theory to predict, and we see that experimentally, if that's true. Okay? We're good? Okay, let's look at a couple pictures of these hybridized orbitals. I think hybridized orbitals are so cool. And here's why. Hybridized orbitals take and they mix. So here's the deal. Let me just give you a little prequel on my beloved carbon. So my beloved carbon, super cool. So my beloved carbon is 1s2, 2s2, 2p2. So 1s2, 2s2, 2p2. Does that ring a bell? What in the world does that even mean? Well, here's what it means. It tells me my principal quantum numbers, my azimuthal, remember this? Okay? And how many electrons are in there. All right, that's what this tells me. It tells me a lot. It's not just one thing I memorize. It actually tells me a ton about carbon. So carbon, on an energy scale, has a 1s orbital. And if you want to make a little box, I'm fine. I don't care. Line or box. You can even make a circle. Make a triangle. Whatever you want. That's an orbital. It holds 2 electrons. And because of Pauli's exclusion principle, they spin pair. And if you hit it with a photon, it excites it to the singlet state. And if it has an intersystem cross, it switches over to the triplet state. Which of those of you who take advanced organic get to learn. Okay? But for us, we have 2 electrons. Spin paired. Okay? Spin paired. Pauli exclusion principle. Boom. I have the 2s. And I have the 2p. But because these are n equals 2, they're close together. So here's what happens. Okay? Here's what happens. Carbon comes along and says, I don't think it really has a brain, but I have 3 different ways in which I can mix 4 orbitals. This is so powerful. This is organic first semester. This is Dr. Nagalis. Okay? I'm this. I'm 1s2, 2s2, 2p2. Okay? And here's why carbon to me is the miracle atom. How many orbitals do I have here? 4. How many electrons do I have here? How many electrons? Ignore this. How many electrons do I have here? 4. How many orbitals do I have?
carbon says one of the ways that I can do this is to take those and to mix them all degenerately or equal energy. And when it does, it populates 4 molecular orbitals with 4 electrons. And what is my electron domain geometry of 4? What's its hybridized orbital set? Oh, hey, that makes sense. It's an spp, or an sp3 carbon. How cool is that? So carbon says to hydrogen, hey, since I'm in a really bad situation over here, I need 8 electrons, I've only got 4, why don't you come over here and share with me? And so hydrogen says, cool, I'll come share. And another hydrogen says, oh, cool, I'll come share. And another hydrogen, cool. And it makes methane gas, okay? So that's why methane then looks like that, and that carbon is an sp3 carbon. Wow, mind-blowing. Now, carbon can also say, hey, wait a minute, I have another way that I can do this. I can leave one out. I can leave a 2p out, and I can mix this way. Well, that's kind of cool. And I still have 4 electrons, but watch. What is my electron domain geometry of 3? What is it? SPP, SP2. Oh, that makes sense. It's SPP, or SP2, but it leaves a 2p orbital unhybridized. So watch what happens when carbon does this. Carbon comes along and says, okay, carbon, now let's do an oxygen just to have something different. Okay, oxygen, and hydrogen, I'm happy. So carbon says to hydrogen, share with me. Carbon says to hydrogen, share with me. Carbon says to oxygen, share with me. But now oxygen and carbon both say, hey, we have 1 orbital that's unhybridized. Hey, I got an idea. Let's go ahead and share up there as well. And we'll call that a double bond. Okay? So that's a pi bond. That is a double bond. Notice what happens here. Carbon has 3 electron domains. 1, 2, 3. Oxygen has 3 electron domains. 1, 2, 3. What is 3 in hybridization? sp2. So this becomes an sp, I'm using Christmas colors. How cool is that? That's an sp2 carbon. Notice how carbon, sp3 if it has all 4. It's an sp2 if it has 3 and a double bond. Now watch what else carbon can do. If I had blue, I had orange, cool. So carbon says, well, wait a minute. I got one more way I can do this. What happens if I mix that and just that and leave out those 2? Well, if carbon does that, it becomes this. And carbon says, oh, I still have 4 electrons, so let's go ahead and share. And let's go ahead and share. And so an example, this was carbon coming in with a nitrogen and a hydrogen. There. Carbon says, cool, let's go ahead and share hydrogen. Let's go ahead and share nitrogen. But nitrogen says, hey, I've got more electrons. Carbon says, I've got 2 more too. So let's go ahead and let's share up here, and let's make a triple bond, and let's make cyanide gas. Cool. So carbon, notice, it is a linear geometry. It is an electron domain of 2, and it is an sp hybridized orbital because I brought together an s and a p. How cool is that? And that's what makes carbon the miracle atom. Because you can make alkanes. This is an alkane. You can make alkenes, all kinds of alkenes. That is an alkene. This is an alkyne. That's actually acetylene, okay? So carbon can make all sorts of amazing molecules because it can hybridize in an sp3, an sp2, or an sp. It can do that with carbon itself, or it can do it with oxygen, or it can do it with nitrogen. And welcome to organic chemistry, because this is where you get into alkanes, alkenes, alkynes, aromatics, aldehydes, ketones, carboxylic acids, esters, amides, amines. It just goes on and on and on. And it is absolutely phenomenal that if we understand VSEPR through the lens of both electronegativity and hybridized orbitals, welcome to the foundation of organic chemistry. Okay? And that is really cool, because when we start to draw real big molecules, you start to see, oh, that's how we can draw something like ibuprofen and have an idea. That's what it looks like. How cool is that? It's absolutely cool. I don't care who you are. That's cool stuff. All right? I just happen to love it, but I'm trying to show you, or at least, you don't have to love it, but at least appreciate it. Okay? Because I started this entire semester with, this is a window into a brand new world. And that's exactly what we see. My window just gets real small. My window's like right there. Okay? But through that window, you can build life. Okay. Questions? Because we got it complicated. That's all. Oh, let me show you some pictures. Let me show you some pictures of my orbitals at the Grand Canyon.
What is the SP?
Yeah, boom. Okay, that's a great question, Hunter. So, but no, so what happens, not with carbon, go down to like phosphorus, right? So we're 1s2, and this is what's really cool, it's a great question. We're 1s2, 2s2, 2p6, we're full. We drop down to 3s1, 3p, but what happens when we have the 3p? What else do we have along with 3p? 3d. So what happens when you jump up, or when you go down to the sulfur or phosphorus, you have a 3s, 3p, and 3d. So now you look like this. So if sulfur wants to just stay normal, it'll just be a 3s sp3 as well. Okay, it happens to be the 3 sp3, but it's still just sp3. But if it's sulfur and it needs to make 6, then it says, okay, let's go ahead and let's mix all of those.
Well, that to me looks like you'll have one single bond, two or three pi bonds.
Depends on how many electrons are populating that, right? Right? Because if we're sulfur, we're going to be this, right?
Right, but the 3s one would not also be filled by.
No. Oh, yes. This is filled.
I know, but it could be filled with a bond electron.
Yeah.
So
Yeah, it could be a double bond or triple bond.
Yeah, so then wouldn't that mean that the 3s this is a single bond rather than?
No, remember, once they mix, they become degenerate. They're all equal. Yeah. Okay, hang on one second. We got 1 minute. Okay, let me just show you the orbitals real quick. Just a couple pictures. Then we'll pick up the next theory on Friday. So if you look at these, polarity, blah blah. There's polar, blah blah. Okay, so here's what actually happens. Well, you know what? I'm gonna pick this up on Friday. Get out of here. Hey, Dr. Chase.